What specific problem does the DriveGPT method aim to solve in the context of autonomous driving, and how does it differ from traditional approaches to behavior modeling?
The DriveGPT method aims to solve the problem of behavior modeling in autonomous driving, specifically predicting the future actions of traffic agents based on multimodal inputs such as agent history states and map information. Unlike traditional approaches that often rely on handcrafted features or specific rules, DriveGPT utilizes a transformer-based autoregressive model that learns underlying spatiotemporal dependencies from large-scale datasets, enabling it to handle complex scenarios more effectively. The model is trained on over 100 million high-quality human driving examples, significantly larger than existing datasets, which allows it to better manage rare or edge case situations that are challenging for autonomous vehicles. Additionally, DriveGPT scales both the model parameters and the training data, demonstrating improved performance metrics and robustness compared to previous behavior models constrained by limited data and model sizes. This comprehensive scaling approach marks a significant advancement over traditional methods, which typically do not leverage such extensive data or model complexity.
Can you illustrate step-by-step how the proposed DriveGPT algorithm works, particularly focusing on the encoder-decoder architecture and the mechanisms involved in predicting future positions?
The proposed DriveGPT algorithm utilizes a standard encoder-decoder architecture to predict future positions of traffic agents. First, the encoder processes multimodal inputs including target agent history states, nearby agent history states, and map information by normalizing these inputs to an agent-centric view and converting them into scene embedding tokens through a pointnet-like encoder. This is followed by applying a self-attention mechanism to fuse these inputs into a set of encoder embeddings that summarize the driving scene. Next, the decoder, inspired by large language models, LLMs, takes the embeddings generated by the encoder and the historical agent positions as inputs. At each prediction step, it cross-attends to the encoder embeddings to predict the distribution of the next agent position. The output is a set of discrete actions represented as verlet actions, which are then mapped to positions to ensure smooth trajectory predictions. The training process employs teacher forcing, where ground truth future positions are used to guide the decoder, allowing for parallel prediction of all future steps. This step-by-step mechanism enables DriveGPT to effectively model and predict the behavior of traffic agents in complex driving scenarios.
Provide a simple yet illustrative example that demonstrates the inner workings of DriveGPT, detailing how it processes input data and generates predictions for a traffic agent's future states.
DriveGPT processes input data through a standard encoder-decoder architecture, where the encoder fuses multimodal inputs, including the target agent's historical states, nearby agent states, and map information, into a set of scene embedding tokens. For example, when predicting the future state of a traffic agent, DriveGPT first normalizes these inputs to an agent-centric view and generates encoder embeddings that summarize the driving scene. The decoder then takes these embeddings and the historical agent positions to predict the distribution of future positions step by step, utilizing a method akin to autoregressive models. Specifically, at each time step, it cross-attends the encoder embeddings with the agent embeddings to forecast the next position, represented as discrete actions derived from the predicted verlet actions. This process allows DriveGPT to generate smooth and accurate trajectories, effectively handling complex interactions in real-world driving scenarios.
What are the theoretical and practical benefits of using the DriveGPT method over existing behavior modeling techniques? And how do these benefits impact safety and robustness in autonomous driving systems?
The DriveGPT method offers significant theoretical and practical benefits over existing behavior modeling techniques, by leveraging a large-scale dataset of over 100 million high-quality human driving examples and scaling model parameters to over 1 billion. Theoretically, it establishes empirical driving scaling laws that demonstrate improved performance metrics as both data size and model parameters increase, particularly in handling rare or edge case scenarios that are critical for safety in autonomous driving. Practically, the model's autoregressive architecture allows for more accurate trajectory predictions, as evidenced by its superior performance on the Waymo open motion dataset, where it outperforms prior state-of-the-art models in motion prediction tasks. These advancements contribute to enhanced safety and robustness in autonomous driving systems by producing map-compliant and collision-free trajectories, effectively managing complex interactions in real-world driving scenarios. Overall, the combination of extensive data and a scalable model architecture positions DriveGPT as a leading approach in improving the reliability of autonomous vehicle behavior prediction.
How was the performance of the DriveGPT model validated in the experiments? Please discuss the datasets used, metrics for evaluation, and any comparative benchmarks that highlight its effectiveness.
The performance of the DriveGPT model is validated through a series of experiments using both internal and external datasets. The internal dataset consists of 120 million high-quality human driving demonstrations, while the external evaluation is conducted on the Waymo Open Motion Dataset, WOMD. Evaluation metrics include standard geometric metrics such as minimum average displacement error, min-ADE, minimum final displacement error, min-FDE, and miss rate, MR, which assess the accuracy and reliability of predicted trajectories. DriveGPT is compared against the state-of-the-art MTR model, demonstrating significant improvements across all geometric metrics, particularly at shorter prediction horizons, with over 12% enhancements in min-ADE and min-FDE, and a 20% reduction in miss rate. Additionally, the model's performance is further validated through pre-training on the internal dataset, which yields additional gains despite the distribution shift when fine-tuning on WOMD, underscoring the effectiveness of data scaling in enhancing model performance.
What specific results were achieved with the DriveGPT model, particularly in the motion prediction task? Discuss any improvements over state-of-the-art methods and the implications of these findings for future research.
The DriveGPT model achieved significant improvements in the motion prediction task, outperforming the state-of-the-art MTR model across all geometric metrics, particularly at short horizons, 2s and 5s, with over 12% enhancements in min-ADE and min-FDE, and a 20% reduction in miss rate. These results were obtained despite a large distribution shift between the internal dataset used for pre-training and the public Waymo Open Motion Dataset, WOMD. Additionally, pre-training on the internal dataset yielded up to 4% further gains, demonstrating the effectiveness of data scaling in enhancing model performance. The findings suggest that larger and more diverse training datasets are crucial for improving the robustness and accuracy of behavior models in autonomous driving. This underscores the importance of continued research into data scaling and model architecture to further advance the capabilities of behavior prediction systems.